For centuries, we've looked to the stars and wondered, is there an edge to the universe? What if the answer is both yes and no? We're about to explore the great mystery of what lies at the final frontier of the cosmos, a place our eyes can never see, a boundary that is constantly moving, and a reality that is far stranger than any fiction. Get ready, because the universe is about to show you its limits. Before we begin, a quick favor. Give this video a like and subscribe to the channel. It helps push this mind-blowing content to more space lovers. And tell me in the comments, where are you watching this from? Okay, now let's begin.
In the vast, sprawling expanse of the cosmos, we are prisoners. Our vision is limited, confined within the boundaries of what scientists call the observable universe. Everything we can possibly see, from the interior of our room to the most distant galaxies visible through our most powerful telescopes, is a part of this bubble. The radius of this observable universe is a mind-boggling 46.5 billion light-years. But here's the paradox. The universe is only 13.8 billion years old. How can we see anything that's farther away than the time light has had to travel? The answer lies in the expansion of the universe. The very fabric of space is stretching, carrying the light-emitting objects away from us. So the light we see today left its source a long time ago, and the source itself has since moved much farther away. This creates a cosmological curtain, a barrier beyond which lies a universe that, to us, is simply unknowable. While modern cosmology suggests the universe may be infinite, we are forever trapped within this observational sphere. The philosophical problem of what lies beyond this boundary is a challenge that pushes our thoughts to the very edge of human comprehension.
The expansion of the universe doesn't just make things distant. It creates barriers that we can never cross. The Hubble horizon is a theoretical point in space, about 14.5 billion light-years away from us, beyond which objects are receding from us at a speed faster than light. That means that the light they emit, no matter how bright, will never be able to reach us. It's a cosmic race that light can never win. For a photon trying to reach us from beyond this horizon, it's like running on a treadmill that's speeding up. The farther it gets, the faster the space between us stretches, and the farther away it gets. This makes it seem as though the universe has a hard limit, but in fact, it is just the light itself that is limited. This expansion also affects another horizon, the event horizon. This is a boundary that sets a limit for any signal we emit. The current radius of this limit is 16 billion light-years. If we were to send a signal to a galaxy beyond this event horizon, that signal would never, ever reach its destination. The space between us would expand so quickly that the signal would become infinitely long and would never be detected. In the very distant future, the Hubble and event horizons will merge, forming a new, unbreakable boundary. We will be cut off from the rest of the universe, a lonely island of galaxies in a vast, silent sea. It is a terrifying thought that our ability to communicate and learn about the universe may be finite.
We've established that the cosmic horizons limit what we can see with light. But what if we could use something that isn't light? What if we had guides that could travel through the cosmos unimpeded by matter and unaffected by the expansion of space? Scientists are now exploring just such a possibility with neutrinos and gravitational waves. Neutrinos are tiny, fundamental particles with almost no mass and almost no interaction with matter. They are formed from violent cosmic phenomena like nuclear processes in stars and supernova explosions, and they can travel for hundreds of billions of light years at almost the speed of light. because they have almost no interaction with matter, they can travel straight through planets and galaxies, carrying data about distant events that we could never see with our telescopes. In addition to neutrinos, gravitational waves are our other guide beyond the veil. These waves of spacetime, predicted by Einstein's theory of relativity, are created by the acceleration of massive objects like colliding black holes or two neutron stars rotating around each other. These waves travel in all directions at the speed of light, carrying information about the events that created them. The development of ultra-sensitive detectors like LIGO has allowed us to capture these waves, and with them, we have been able to hear events that happen billions of light years away in a part of the cosmos that is well beyond our visual horizon. The development of technology to capture these signals is our key to unlocking the mysteries of the entire universe.
With the universe setting its own limits and expanding relentlessly, we are forced to ask a chilling question. What is the ultimate fate of the cosmos? There are several theories, each more terrifying than the last, that attempt to answer this. The first is heat death. Based on the second law of thermodynamics, this theory suggests that the universe will expand forever until all energy dissipates and a state of maximum entropy is reached. Stars will stop forming, galaxies will become too far apart to interact, and the universe will become a cold, dark, empty void. All energy will become evenly distributed, and no work will be possible. It's a slow, quiet, and lonely end to all of existence. Another theory, born from the accelerating expansion of the universe, is the Big Rip. This theory suggests that the dark energy driving the expansion will become so powerful that it will overcome all other forces. First, it will tear apart galaxies, then solar systems, then planets. Finally, it will tear apart the fundamental forces that hold atoms together, ripping apart the very fabric of matter itself. The universe will end not in a quiet whimper, but in a violent, chaotic tear. An explosive end to all reality. While these theories offer a terrifying glimpse into the future, they are still just that, theories. But they do force us to confront a fundamental question. Is our universe doomed to end in a blaze of glory, or a silent freeze? The mystery of our solitude in the cosmos is one of the most profound questions of our time. The Fermi paradox asks why, in a galaxy with hundreds of billions of stars and billions of years of history, we haven't found any other intelligent life. One of the most compelling and chilling answers to this question is the dark forest hypothesis. This theory, popularized by a science fiction novel, suggests that the universe is like a dark forest filled with silent hunters. Every civilization is a hunter, hiding and listening. If a hunter discovers another, it is in their best interest to strike first before the other has a chance to strike back. According to this hypothesis, all advanced civilizations are hiding in fear of being attacked for their resources. Communication is a dangerous act that gives away your position and invites destruction. Our radio signals, our greetings, our attempts to make contact could be the very thing that leads to our demise. The silence we hear then isn't a sign of an empty universe. It's a sign of a very, very full one. It's a silent, terrifying battlefield where every civilization is locked in a desperate struggle for survival. It's a theory that, while not scientific, provides a logical and chilling explanation for the great silence of the cosmos.
We've been exploring the vastness of the universe, but what about the things that exist beyond our current understanding? The things we can't see, hear, or measure? The universe is a place filled with unknowns, from the nature of dark matter and dark energy to the possibility of extra dimensions and alternate universes. These ideas are not just the stuff of science fiction, they are the frontier of modern physics. What if the universe isn't just one reality, but a part of a larger multiverse? The multiverse theory suggests that our universe is just one of many, each with its own laws of physics and its own history. These other universes, called branes in string theory, could coexist, separated by a higher dimensional hyperspace. The universe we see, then, is not the whole picture. It is just a single bubble of reality in a cosmic foam. The possibilities are endless. There could be universes where gravity is stronger, where time runs backward, or where life as we know it is impossible. This idea is a humbling reminder that what we know and what we can see is just a tiny fraction of the whole picture.
The Big Bang is the scientific origin story for our universe, but it leaves a profound and lingering question. What happened before the Big Bang? It's a question that, according to our current understanding, is meaningless. Time itself began with the Big Bang, so asking what happened before is like asking what is north of the North Pole. But that hasn't stopped some of the greatest minds in physics from proposing theories that attempt to answer this question. One of these is the Big Bounce theory, which suggests that the Big Bang was not the beginning of everything, but rather a rebound from a previous contracting universe. The universe expands, grows, and then collapses back on itself, only to bounce back and start a new cycle. Another theory, the no-boundary proposal, suggests that the universe did not emerge from a singularity. Instead, it emerged as a kind of four-dimensional sphere, with the Big Bang being a smooth point on that sphere, not an absolute beginning. This theory, championed by Stephen Hawking, gets around the singularity problem by suggesting that the universe has no boundaries, just as the Earth has no edges. These theories, while speculative, are a testament to our ongoing quest to understand our origins and the nature of the cosmos itself. The mystery of our universe is not just in the big things, but also in the small. What if every electron in the universe is the same electron? This is the core of the one-electron hypothesis, a bold and unconventional concept proposed by physicist John Wheeler. It suggests that every electron in the universe is a single particle, traveling through a continuous trajectory in space-time. When the electron travels forward in time, it appears as a regular electron. But when it travels backward in time, it manifests as its antimatter twin, a positron. This is a mind-bending idea that suggests a level of interconnection among all particles that is far beyond our current understanding. The beauty of this idea is its simplicity. It offers an elegant explanation for why all electrons possess identical properties, because they are, in fact, all the same particle. While this theory faces significant challenges, it forces us to reconsider the very nature of individuality in the universe. If it is true, it means that the fabric of our reality is unified through a single particle traversing time, and that the distinction between individuality and universality may be an illusion.
We have journeyed to the edge of the universe, and we have peered into the deepest mysteries of the cosmos. We have explored theories that challenge our very understanding of reality, from the Big Bang to the one-electron hypothesis. The search for what lies at the edge of the universe is not just a scientific quest, it is a philosophical one. It is a journey that forces us to confront our own limitations, our own fears, and our own place in the cosmos. But in that journey, we also find a profound sense of wonder. We are a species that, despite being scared of the unknown, has always dared to look into it. We have a boundless curiosity that drives us to explore, to discover, and to push the boundaries of what is possible. And in that spirit of exploration, we may one day find the answers to all of our questions. We may find out that we are not alone. And in that moment, the universe will no longer be a mystery. And for all the myths you've ever heard, this story has proven that some parts of our past are not a myth now.